So
perfect.
I am recording now.
Perfect. So we have 21 attendees now. So and 1 minute left. So
all right.
so it's 8 o'clock. So I think we start, Emily. So hello everyone and welcome to Swedron's webinar. Today we have a special guest with us. It's Emily from Micasense. Hi, Emily.
Yes, hi Annette. Thanks for having me.
Thank you for coming. So please, I think I'll do so that I handle it over to you now.
All right, I'll get started.
Directly. Okay, we can do if the attendees have some question, you can write it in the chat, and then Emily and I together take the questions as they come. Is that's okay for you, Emily?
Yeah, that definitely works for me. So yeah, if there's any questions that come up, just type them, as they come up, and we can pause and I can answer those as we go along.
Perfect. So please get started.
All right. So let's show the agenda here. So yeah, as Annette mentioned, my name is Emily Shushelski, and I'm a channel sales manager with Micasense. So today I wanted to start off with an overview on Micasense for those that aren't already familiar with the company, a brief overview on multispectral sensors and what they're capturing, and then go into more detail about our specific product lineup. So we've got 3 sensors. I can share some examples about how they're all best used and what they're best suited for. And then I've got some examples as far as data examples for forestry, one with stand counting of young trees, one for identifying bark beetle infested trees, and one related to fire mitigation, specifically identifying trees that could be a fall risk near power lines. So Micasense as a company, we're based in Seattle, Washington, so on the West Coast here in the US. And we've been around since 2014. That's when we came out with the first red edge model, so the 5-band multispectral sensor. And we've been continuing to design and manufacture the sensors out of our Seattle office here. As you can see, we're a smaller team. So the way we've been able to build a global brand and expand usage of our sensors globally is through our really strong reseller network. So we're represented in 60 countries. Swedron is our certified partner in Sweden. So happy to be working with them today. Something about our sensors that makes us pretty unique is that we are platform agnostic with our products. So that's both on the drone side and on the software side. So not tied to any one drone when we're developing our sensors, keeping the weight minimal and the form factor size small are really important so that we can have a variety of drone integrations that are possible. And then same goes on the data output side. You try to keep that open so that a number of different third-party softwares can use the metadata to do calibration and process the imagery. So a brief overview on multispectral for those that maybe aren't familiar yet. The graph on the right-hand side that we see there is showing, typical, when the sun is beating down on a plant. that visible and non-visible light is either absorbed by the plant and used for photosynthesis. It can be transmitted through the leaves, or it can be reflected back up. So that last part that's reflected back up is what the multispectral sensor is capturing. And the majority of what's going to be reflected up is near infrared or non-visible light. So that's what makes it different than a typical kind of RGB sensor that's just using the visible bands. And the bottom right there, you'll see a graph for as far as a typical reflectance curve for a plant. So a healthy plant, you'll see the reflectance curve is that green line there. In the visible light, there's a spike in reflectance for green. That's why it appears green to our eyes. Not as much reflectance in blue and red, since that light is more absorbed by the plant and used for photosynthesis. And then a big increase in light reflected in the near infrared. So that will change as the plant is stressed, whether that's because of a nutrient deficiency or water stress, pest pressure. So the dotted red line shows how that will typically change. We'll start to see more reflectance in blue and red because the plant's not absorbing that light as effectively. And then a reduction in the reflectance for the near infrared. So that's kind of what allows us to identify stress early on before there's visible signs of stress, to the human eye. So these are the 5 multispectral bands that have been selected for red edge. So when you align them on this typical reflectance curve for a plant, you can see that they're very intentionally situated at these specific points, whether it's the dip in reflectance for blue, right at the peak of reflectance for green, red edge, which is right in between the red visible and the non-visible, and then near infrared as well for the 5th band. So with these 5 bands, we're able to input them into various formulas to give us vegetation index values. We can also assign a color to the near infrared light and do a false color composite. So all these different things are kind of the analytics or outputs that you can get to visualize and get insights from the multispectral data. So 2 common indexes, vegetation indexes, are NDVI and NDRE. So I just wanted to share those equations to show how those bands are used. So essentially just inputting for NDVI, the near infrared band and the red band. And that's going to be giving us information on plant biomass. So really good for young plants as the leaves are growing, the canopy is growing, being able to identify areas where plants are not going as quickly as surrounding plants, whether that's because of a soil health issue or whatnot. It's going to be able to identify differences in biomass. And then as the crop canopy matures, or you're looking at a tree canopy that's fully grown, then looking at something like NDRE is going to be more useful, provide more information there. So that's the same kind of a formula as NDVI, except we're switching out one of the bands. Instead of red, we're looking at red edge, and that's going to give more information on chlorophyll content in the plants. So that's better for mature crop canopies to see those subtle changes due to stress. So one important consideration for any kind of multispectral sensing is the radiometric calibration process. And the reason that's important is to ensure that you can be able to compare the maps over time to do a time series analysis, which is going to be important for most kind of use cases, not just looking at a single snapshot in time, but comparing maps side by side from different flights to look at the plant growth during the season. And so the way that we're able to do that is by using 2 different tools, and these are provided with all of our camera kits. So one of them is the panel that you see on the left there. It's our calibrated reflectance panel. You see the white material there. It's our target. Essentially, we know for that material what the reflectance values are for the 5 different bands for the sensor. And we've got the QR code there that will provide the specific values for each panel, because each panel will be slightly unique in their values. And then the panel is used in combination with our light sensor, which is on the right here. So the light sensor gets mounted to the top of the drone. It's unobstructed by any shadowing from propellers from the drone. And we can see the small white sensors there. There's a variety of those sensors on the DLS, and it's essentially capturing every time the camera below is capturing. So it's gathering information at a second by second basis on the irradiance, and as well as where the sun angle is in relation to the drone. That's why you see there's kind of all slightly different angles for the different sensors there. So when it goes to actually flying with the multispectral, our recommendations for lighting to get best results are to keep it consistent. So that's the ideal lighting conditions are going to be consistent, either uniformly, a sunny day like we see in the top image, or a uniformly overcast day like we see in the bottom image. What we want to avoid is a situation where it's sunny, but there's a couple large clouds that are rolling through the sky that would cause a deep shadow on some areas that you would want to be mapping. Anytime you have deep shadows, that's going to be really difficult to correct for. Also, for the reason of deep shadows, we recommend flying within 2.5 hours of solar noon. So, flying within a couple hours of noon will reduce the shadows that you might see in the resulting map. When it comes to the flight, besides setting up the camera to capture, what we also recommend is taking a panel capture before and after the flight. So with that calibrated reflectance panel that's provided, once the camera is connected to the drone, it's powered up, just holding the drone over that panel to take a manual capture. And the reason that we ask to do that before and after the flight is so that you can decide which shot to use once you go to process. So you want to use whichever is more representative of the lighting conditions throughout the majority of the flight. And then one last thing to mention about the lighting. It's important to remember as well what the lighting conditions were like during the flight, because when you go to process, most processing softwares will give you the option to decide what you're using for the calibration. And so for a sunny day, we recommend just using the panel. And that's because there's not going to be much variance in the lighting conditions there. Whereas on an overcast day, there's going to be a lot more subtle changes. And so in that case, we recommend using both the light sensor, which that's what the light sensor was developed for, and the panel. So you're getting both the reference shot from the panel, as well as the kind of second by second breakdown from the light sensor on those cloudy days. And this is a good instance of how the light sensor can be used. We've got a cloudy day, you can see in the bottom image there for reference, but there was some areas where the clouds had kind of thinned out a little bit. So it ended up being during the flight that the clouds parted for a moment, and we ended up getting a sunspot in the corner of the field. So that was something that the DLS was able to easily correct for. So you can see that on the right-hand side. All right, so this is the full sensor suite. We've got the red edge sensor that I mentioned, the Ultim sensor, which has our highest spatial resolution. That's why it's got the larger lenses. And then the dual camera system, which has the highest spectral resolution. So I'll go through each of these individually. So first up with red edge, we've got the 5 multispectral bands there that I mentioned. Flying at 120 meters, you'll get a resolution of 8 centimeters per pixel. And then the lower you fly, the better that resolution will get. We have a nifty flight calculator on our website that can be used, entering in the flight altitude to see what the resulting GSD would be, the ground sample distance. We've made a couple updates to the Red Edge kit recently. One of them was to expand the storage capability. So it used to come with a 32 gigabyte SD card. It's now been expanded. We've made a firmware update that allows for this, and now we're able to use 128 gigabyte SD cards. We've also reduced the size of our reflectance panel. So it used to be much larger. We've shrunk it down, so it's really just enough to encase that white target material. So it's a lot easier to carry around and transport. So sample data from Red Edge, the main kind of outputs you're going to get with the sensor are the general RGB composite to get a kind of bird's eye view of the area that you're investigating, as well as the variety of vegetation indexes that you can get from utilizing the 5 different bands. So how that's typically used is as a kind of targeted scouting tool. So for agriculture, if you've got a large farm, for forestry, this could relate as well, looking at larger areas and identifying where there's potential issues that you want to send people to on the ground to investigate further. So in this case, in this example, I've got an agricultural example. This is a plum orchard in California, and they were flying the blocks to assess uniformity across the field. And what they found, looking at a chlorophyll map here, was really low values in red on the last 4 rows. So that was something where they might have expected lower values at the very edge row, just because of dust that gets kicked up from different machinery and cars driving on that road, surface road. However, they were really surprised to see those 3 additional rows to see such low values. And especially when you're looking at the chlorophyll map in relation to the RGB composite, it doesn't appear that there's any yellowing or visible stress in the RGB. So this is early stage chlorosis essentially that's identified. The one thing they knew was different about these last 4 rows is that they were irrigated with a different water source. So that was the first thing that they did was test that water. It turned out it was really high in salinity. So that's what was causing the trees to become chlorotic. So they're able to quickly switch out the water source there to what was used for the rest of the field. And within a couple of weeks or so start to see recovery in the trees. So able to identify that issue and the extent of the issue early enough that something could be done to let the trees recover. Another great use for Red Edge is for planning input decisions. So whether it be fertilizer application or pesticide application, things like this. So the 2 examples I have are for fertilizers. The first was actually monitoring an application. So an application that had already been planned and was done. The grower had contracted a third-party applicator to apply nitrogen to their rice field. So they wanted to fly a week or so after the application to assess the application essentially. So 10 days after they flew and got this NDRE map. So the highest values we see in this map appear as blue. So you can see it's definitely not the uniformity that you would expect to see. We see some striping here, indicative that there wasn't enough overlapping between the passes of the application equipment. And then additionally, we see some low values here or mid-range values of NDRE where it looks like there wasn't fertilizer applied. So that's something that the grower then has, a bird's eye view of everything that's happening in the field, something to go back to the applicator with to resolve that issue. On the second example we have here, this one is more about planning of a fertilizer application. So in this case, the problem had already been identified, which was a nematode infestation in this peach orchard. But they wanted to see what was the extent of the infestation, because one of the control methods is to apply nitrogen. And so they didn't want to apply it to the whole block because we've got some areas that are here that are performing quite well. So they don't need that additional nitrogen. So they were able to use these NDRE values, identify the low values here in orange, red. And that's where they focused the nitrogen applications. So after that kind of variable rate application, they flew again and were able to see that a lot more uniformity was achieved through that particular decision to apply nitrogen to those areas. Dual camera system is our next sensor that I wanted to discuss. So this is our newest offering. It's taking the standard Red Edge that we have and adding an additional Red Edge MX Blue, what we're calling it. So the blue camera has 5 new bands, 5 new center wavelengths, and they were added to complement the current red edge. So you're getting a total of 10 narrow spectral bands. And what we wanted to do with that, with the two sensors, first of all, is to offer an upgrade opportunity for current customers if they have discovered that they need the, could utilize the additional spectral resolution. They're able to add the blue camera to this, to their setup. And additionally, for current customers, if they start out with the red edge and then realize for certain projects that the spectral resolution is needed, there's always the opportunity to add the blue camera. With the 10 total bands, you can see the list here of we've got 2 blue, 2 green, 2 red, 3 red edge, and 1 near infrared. So in choosing those bands, we wanted to correlate with satellite imagery. So specifically Sentinel-2 and Landsat-8. So they're correlating with those bands from satellite imagery that's been available globally, freely available. So there's already a wealth of research that's been done utilizing those bands. So dual camera system is offering a drone-based system to complement that, to be able to offer the higher spatial resolution where needed, whether it's to validate satellite models or to increase the coverage of ground truthing efforts, things like that. So it's something that can be easily complement satellite data for looking at larger areas. So some sample data from dual camera. With the addition of the 5 new bands, one of the main kind of new capabilities that unlocks is more capability for species classification. So that's the first example I have here. So 10 bands are enhancing the capability for species classification, namely with the new red edge bands. So having the 3 red edge bands, we found has been especially helpful for identifying unique spectral signatures between different species in a scene. So we see an example here of a forested area where you can clearly see we just created a false color composite, assigning a color to one of the new red edge bands. And you're able to see the 2 different tree species as well as 2 different grasses in that scene. So this is kind of the basic start to a classification workflow, identifying which bands bring out the most variation between the species in the scene, and then working the classification from there. So this is an example of a completed classification that we've done. And this one is on the agricultural side. So it's ended up being weed detection. And in this case, it was a spearmint field where there was a specific noxious weed, Canadian thistle, that the grower wanted to identify. It's something that looks really similar visually to the spearmint crop. So actually this grower has already had a service provider flying for a couple of years with the red edge sensor and doing weed detection, generating maps so they can guide their herbicide applications. However, in this case, because the weed looks so similar to the crop, they weren't able to identify the weeds to the level of detail that was required. So while they could see some larger outbreaks, like you might see here in these darker green spots, they weren't able to see every instance, and that was really important for the herbicide planning and in general before harvesting to ensure all the weeds had been removed. And so what we were able to do is use a 10-band system, and using that additional spectral resolution, identify even small outbreaks of this weed, as well as a secondary weed in the field, which was wild mustard. So this is kind of an example that we did. This field was in transition to organic, so it did have more weed pressure. And we were able to see here, once the classification is finished, the vector is overlayered over the RGB composite, and you can see all the instances of the Canadian thistle in pink, and then the wild mustard in light green.
Okay. Emily, I think you have a question in the chat. Do you see the chat window?
Great. Okay, let's see. Yeah. All right. Question: is it possible to minimize shadows or shadows that have formed on the Ortho Mosaic, even though a light meter and calibration panel were used? For example, during a long flight, the weather unexpectedly changed. Yes, in that case, the best bet is to use both the light sensor and the calibration panel, like you mentioned. And the light sensor is what's really going to allow to correct for those clouds, hopefully. I've seen some pretty drastic examples, I guess you could say, of a very deep shadow over the field, the rest sunny, and we're able to correct for the majority of it. But in those drastic cases, it might end up being, something at the edge of the field might show up as much lighter, kind of like a sunspot kind of image. So that all being said, it might not be perfect if it's these kind of situations where there's a deep shadow on the field, but it could take an unusable data set to a usable data set if you're using that light sensor, if that makes sense. So it will depend a little bit on what the lighting conditions were like and how drastic the shadow is. But that's what the light sensor was developed for, was to try and correct in as many situations as possible, since we know it's, obviously not always going to be ideal for lighting conditions that can't be controlled. All right.
Yeah, right.
Yeah, thanks.
Thank you.
Thanks for that question. All right, so the last thing I wanted to mention for dual camera is the satellite comparison. So as I mentioned before, it correlates with Sentinel-2 and Landsat-8, but I wanted to provide a visual comparison, seeing the different spatial resolutions side by side of how the dual camera can be used to either for ground truthing efforts or to validate satellite models. And then the last sensor we have here is the Ultim. And this is our highest spatial resolution. It uses the same 5 multispectral bands as Red Edge. But when you're flying at 120 meters, you'll get 5 centimeter per pixel resolution as opposed to 8 centimeters per pixel like you would get with Red Edge. And then similar to Red Edge, the lower you fly, the better the spatial resolution will be. The other consideration with Ultim is that it has a thermal band as well. So a 6th thermal band. And we've integrated a FLIR lepton unit. And so that's what is used. It's radiometrically calibrated. It is a coarser resolution, so 81 centimeters per pixel for that. And that's because at 120 meters, and that's because the primary use case for the thermal is to identify water stress across a field, or to assess irrigation systems, to identify inconsistencies or inefficiencies in the irrigation systems. So some sample data from Ultim using both the multispectral and the thermal band. So one great application we've seen for Ultim is to be used in field trials. So whether that be university research or private companies that are developing products to increase yield, anything where you're going to have small trial plots and you're assessing performance, different traits across those plots. You'll be able to fly throughout the growing season with Ultim and be able to gather that quantitative data on those plots. So for example, one, flying early on in the growing season to do an early emergence counting. So that's the example you see here, early emergent corn. And you can fly low to get the highest resolution with Ultim. So in this case, we flew at 20 meters AGL. And so we got 0.9 centimeters per pixel for the resolution, and we're able to do a plant count and get the early emergence rates. And then you can also continue to fly on as the crop canopy matures and do something like an average plot vigor. So we can do that with NDVI, and we've seen that in the second image here. So averaging the NDVI values across the plot once those plot boundaries have been identified. And then using the thermal band, we're able to do some, get some insight for irrigation planning as well. So in an agricultural setting, the crop water stress index is really useful. That's basically taking into account the thermal map you're getting, which is reading the crop canopy temperature, and then taking that in relation to the ambient temperature. And so the output looks something like this. This is an example from one of our customers in Chile. And they flew a kiwi orchard the idea there was to, water in that region is pretty scarce, and they want to be very careful and where they're applying only where needed. And so what they ended up doing is flying with a thermal, identifying the two different zones. The zone 0 in pink is the water stressed, is showing water stress in those plants, and zone 1 not as much. So they were able to use that to guide which areas of field are irrigated. And then another application for the thermal is to monitor irrigation systems, whether that's a drip irrigation system or overhead sprinklers. We've got 2 examples of that here. So on the left-hand side, we see they have sprinklers set up that are moving in a circular pattern, rotating on a pivot. However, essentially what you're seeing here in the thermal is that the coolest areas are purple. So at the edge of the pivot here is where the most water is applied. So that's what's showing up as the coolest. However, in this specific area, we're just seeing a line instead of the circle. So that's indicative there that the sprinkler is jammed and it's not completing that full rotation. On the right-hand side, the other example, we're seeing overhead sprayers. So this was flown shortly after water had been applied. So the cooler areas are once again showing up as dark purple. And we're able to see, pretty uniform in this area throughout these, this half of the sprayer. And then in this area, we're starting to see a little bit warmer values. And that would be indicative that there's probably these 2 nozzles are either partially or fully clogged. So an easy way across a large, if you're looking large scale, to quickly identify areas where there needs to be repairs in the irrigation system. All right, so that's a brief overview of the 3 different sensor kits and how they're kind of used. Now I wanted to go into more detail on what comes included in the camera kit and what the drone integration options available are. So I'll start off with Red Edge and Ultim, since those kits are pretty similar as far as what's included. So it'll come with either the Red Edge or the Ultim camera, depending on the kit. It'll come with a lens cover. So that's used to protect the lenses from dust and any scratches when the camera's not in use. The light sensor, which in addition to having the irradiance sensors there, it also has a GPS embedded. So that's what we use to geotag all of the imagery. There's an assortment of cables. The main one that's used is this cable here, and that's to connect the light sensor on the top of the drone to the camera on the bottom. It all comes included in this hard carrying case for transport. The only thing that can't fit inside the case is the reflectance panel, so that is included separately. And then as far as integration, if it's a custom integration, this kit would be all you would need. We've got integration guides with recommendations for installation. But if you have a DJI drone, we do have a variety of ready to go kits, and we call those our quick mount kits. They will connect the camera to the drone power source, so no extra battery pack would be required in those cases. These kits we've got compatible for the Inspire 2 model as well as the Matrice models. So for the Matrice 100 and 600, for older models, those might not come included with the Z30 gimbal adapter. So that's one piece that's not included in our kits that will be required. Essentially, for all of these different models, the gimbal adapter that's used, or the gimbal port style, is the Z30 that will work with our kits. So that's just a consideration for the M100 and 600 to make sure that's included. It's a DJI part. And then for the M200 and the 210 models, our kits are compatible with those. The only caveat is that it's not compatible with the M210 RTK. And that just has to do with how we mount the light sensor, since the RTK antennas are kind of where we would normally mount the mast for the light sensor. And then we do have a kit for the latest, the Matrice 300. So I've got a picture here of what that looks like on the Matrice 300. We've got the light sensor here mounted on top of the drone. And then the camera itself can either be used on gimbal port 1 or 2. And then there is space for an additional camera. So if you did want to have a dual payload flight, that would be a possibility. The camera is, unless you have a skyport, which I'll get to in a second, the camera is set to trigger itself. So you could have the drone trigger the other payload on gimbal 1 and have the Micasense sensor on gimbal 2 and fly both at the same time.
Okay, Emily, you have a question in the chat again about Phantom.
Okay, so is there any adapter for smaller drones? For example, the Phantom. Yes, there are. Micasense doesn't produce a integration kit for that, but some of our resellers have. And there's been, for instance, there's one of our customers in the US has developed one. So they are available, it's possible. The reason that we don't have our own kit is just because the RGB camera that comes with the Phantom is fully integrated and it's not removable. So it makes it a little bit more difficult to, create a simple mount for the sensor to connect it to drone power. So you do have to have a separate battery pack to power it, and a way to, secure it to the legs of the drone, so you're not opening up the drone to integrate the camera. So there are options available, however, not directly through Micasense.
Okay. And then you have another question from Piotr.
Yes, let me see. So could you say more about the 12 directional sensors built into the DLS2? Directional sensors can be understood as more precise, determining the direction of the flight than GNSS. How do they work? The magnetic field. So yeah, the sensors on the DLS2 are at the slightly different angles that you can see here. So that's more to determine for the radiometric calibration, the position of the sun in the sky in relation to the drone, for specifically for the calibration process. So not as much to do with the GNSS. How do they work, the magnetic field? Yeah, that's basically my limited understanding, I would say, is that it's taking into account the sun angle as well as the irradiance measurements from the 12 sensors and using those both in tandem. It's writing it all into the metadata of the sensor, so written into the TIFF files, and then that's used in the various processing softwares. Additionally, we do have we've got a GitHub as far as to be able to access that information yourself as well. I know especially some researchers like to have access to all of that information. So that's something that's available on our GitHub. So yeah, I don't know that I can provide too much more information. It's a little bit beyond my understanding for that one, but the GitHub might be a good next place for additional information.
Okay, good, thank you.
All right. All right, so for Dji integration, the other option that's available is the Skyport. And that one is a more permanent integration. So whereas the quick mount kits, they're going to connect the camera to the power source of the drone, and they're removable. There's just 2 screws that secure it to the back of the camera. Whereas for the Skyport, it comes already fully attached, permanently attached, like you see here. And it's not just connecting to power in this case, it's also connecting to drone communication. So we're activating an SDK license with DJI to be able to have the drone communicate with the camera. And this is going to streamline the workflow essentially. So you don't have to connect to the camera Wi-Fi interface to set it up to trigger itself, then disconnect and go to your mission planner. Instead, you can just go through your mission planner through DJI Pilot and set up the camera triggering settings there. So it does simplify the workflow, and it's a good option if you're going to be sticking to flying with the Matrice 200 or the 300. In addition to having that triggering capability through the mission planner, as you're flying the drone, you'll also be able to, it has a shutter sound that goes off every time the camera captures. So it's that additional reassurance during the flight that everything is connecting and triggering properly. The dual camera is a little bit different than the kits for the Red Edge and the Ultim in that everything comes included. So everything you would need to fly essentially is coming with the dual camera kit. So you're going to see if you get a full kit, it would include the Red Edge and the Red Edge Max Blue fully mounted onto this bracket that has the quick connect piece attached to the back of it. So you just need to twist lock it onto the gimbal port in order to get going. The only part that you need to install is the light sensor on the top here, and then the cable to connect the light sensor and the camera below. So everything comes included there. There's also the upgrade kits that I mentioned briefly before. So if somebody already has a Red Edge M or an MX, they could get a kit that just has this blue camera and the mounting bracket, so they can add their own camera to it. And then as far as integration options, the same DJI models that I mentioned before will work with the dual camera. All right, so for data processing options, I wanted to share a couple options since there are a number of third parties that will, are able to process the imagery. But for reference, these are what the raw images from the sensor look like. So it's just going to be these grayscale images. One TIFF file per band. So every time the camera is capturing, you're going to get from each of those specific bands, you'll get a single TIFF file. And then what the processing software is doing is it's aligning those bands. It's also stitching everything together into Ortho Mosaic. And then it's also running the radiometric calibration. So the companies that we've, as far as third-party softwares, we just partner with those companies, make sure they're utilizing the metadata to do all those processes. The options for local processing are Agisoft Metashape, Pix4D, which Pix4D has Pix4D Mapper and Pix4D Fields, and Simactive Correlator 3D as well. So all three of those are great options for local processing. And then for cloud processing, there's Aerobotics AeroView, and they're focused specifically on tree fruit and tree nuts. Their analytics are specifically for these kinds of crops. And they utilize the Red Edge and Ultim imagery. Drone Deploy has recently added processing for Red Edge and Ultim as well. So for those that are already familiar with Drone Deploy. Altea out of France, they also utilize imagery from all three of our sensors. And they offer different kind of specialized analytics for trial plot analysis. They've done some work in forestry. They do a variety of projects through their specialized projects through their platform. Pix4D Fields is another good option. They offer a quick stitch. So for if you're wanting to fly and then immediately see a process map within 10 minutes or so of the after uploading the data, that's something you can do with Pix4D Fields instead of going back to the office and waiting for a little bit longer to do some of these, the more traditional methods like you might see with the local processing. And then Solvi is another great option for cloud processing as well. So they do cloud processing and they've got some analytics that they provide as well. They just recently came out with a plant stand count feature. So speaking of stand counting, that's one of the examples I wanted to share as far as forestry related. So I do have an example here. So we're based in Seattle. We've done some flights recently in Oregon, in our region, just a little bit south of here. And what we're able to do is flying 2 to 5-year-old stands to do counting. And we're utilizing the multispectral imagery to just identify the trees of interest. So that's kind of where you're going to get more benefit using the multispectral for this, because it is also definitely possible to do stand counting with RGB, and it, probably more common doing that with RGB. But in these cases where you've got younger vegetation, these smaller trees, and there's competing vegetation could be of similar size, it is helpful to have those multispectral bands to do that delineation. So in this case, this was flown with Ultim, and this is the 3-year 2-year-old stand count, I believe. And we processed the imagery and did this stand count in QGIS, so open source software, and entering in different parameters to do the stand counting. So we're looking at only plants of within a certain diameter. We want to make sure that we're seeing a certain spectral response to do the count. So I believe a CAR composite was used in the background. So that's utilizing the near infrared band. And so we're able to enter in those parameters and then run the stand count in a software like QGIS. And so that's what you're seeing here with the GIF is the estimated stand count once those parameters had been entered. And this is another, so that was a smaller subset of the whole area just to show the stand counting automation. But this is the full data set. So this is a digital surface model that was generated with Ultim. And you can see here, in addition to the multispectral information, as well as the diameter that you can information from the flight, you can also see the digital surface model to get some height information. So that's what you see here, the higher area showing up in red. So that's another parameter that can be used to increase the accuracy of a stand count. This is another stand count example. So this one was more recently done. And so we're just starting to do the stand count on this. This is a 2-year stand. So you can see there's, it's pretty difficult to discern the trees at this stage of growth just using the RGB. This is the main area here. If you zoomed in, you can see the trees, but we've also got some competing vegetation here that will affect the view. Using a false color composite, a CAR composite here, we're assigning the near infrared band a red color. So you can see the vegetation then appears subsequently a kind of pinkish color since the plant's majority reflecting near infrared. It's assigning a lot of the red color. So you can start to see a little bit better here where those trees are. But where it really kind of stands out is using NDVI. So I thought this was particularly good for visualizing. You can start to see the dark blue spots where those 2-year-old trees are. And then we can start to threshold like we did in the other example to start to generate the stand count. So in this case, it was simply using information on the area coverage for the vegetation. And we only want to see smaller, smaller diameter plants. And so by doing this kind of basic classification, you're able to kind of threshold out the bigger bushes and whatnot that are also in the scene.
And you have a question, Emily, in the chat about the counting of the trees.
Okay, let's see. So yeah, question about counting the trees. It was a result from some kind of classification. Yes, so let me go back here. Yeah, this one was a classification that one of my colleagues did. And I believe he will be coming out with a YouTube tutorial on this really shortly. So that might be something we can be able to follow up with everyone here with a link for that once that's available. But that was a classification that he did. This one is more kind of beginning stages. This was recently flown last week. So just wanted to show at that really early stage growth what that looks like in the multispectral for this example. So the next example I wanted to share is identifying bark beetle infested trees. So this example is actually coming from Stora Enso. So they agreed to share this information. Graciously agreed to share some of the work that they've done with Red Edge. So they've been flying the Red Edge sensor, so using those 5 bands in areas where there is known bark beetle infestation to kind of identify the severity of that and where the infested trees are, where dead trees are, to to guide management practices, whether that be localized cutting or whatnot. And so the first step for that classification process is to do the tree species classification. So in a stand that's majority spruce, there's also could be, in this case, birch trees as well. So being sure to kind of classify those out if you're just looking to assess the health of the spruce trees. So that's what this first example is here. You can see in the blue or in the green triangles, are the spruce trees. And then in yellow, we do see some birch spread throughout. And in the right-hand corner, you can kind of see zoomed in what that looks like. This is the RGB composite that's zoomed in here. And you can start to see the slight differences in the canopy structure that you're able to see between the different species. And doing this classification, they were able to get 97% accuracy, which is great. And then once that classification is done, moving on to the tree health classification. So in this case, using 3 different parameters or 3 different classifications: healthy center trees, infested center, and dead center. And so that's what we're seeing with the green, yellow, and red dots here. And in the right hand, we can see a zoomed in area of a specific area. You can start to see the dead trees, do appear. They appear so in the RGB as well. The yellow dot here showing a tree that is infested. So it's already showing a lot of signs of stress in that tree canopy versus the healthy surrounding trees. So in instance where they're able to use the different parameters that are gathered from the multispectral imagery to set up this classification and train their model. And in the end, able to get 98% accuracy as far as the tree health classification. And then the last example I have here is for fire mitigation. And this one is specifically related to trees that are a potential fall risk near power lines. So this is an area that we flew in California, and we've got some forested area that borders a residential area. So there is a power line down this road. However, it's a bit difficult to identify in the RGB, especially if it were to be a larger area. And so something that we've done recently is used Agisoft Metashape, one of the local processing softwares that I mentioned earlier. They have a new power line detection tool. So using that and Ultimate Imagery here, we were able to do the auto detection of the power lines on both sides of the road and going up these some of these side streets. So identifying where the power lines are, using that tool, and then layering in the multispectral and thermal information that you can get from Ultim to assess the trees that are nearby. So this is the Ndvi output. You can see the healthiest trees are showing up as blue here as far as pretty dense canopy. And we see some kind of mid-range values here, some of which are trees, some of which could be grasses. So helpful to integrate not just the Ndvi, but also the general height information using the digital surface model. We can also get the thermal information. So the healthier the canopy, the lower the temperature is going to be. So for these for these canopies here where we saw the high Ndvi values, we're seeing cooler temperatures. We do see some hotter temperatures, of course, the rooftops, some of the grasses and areas near the roads. And then using those 2 data layers, we can start to threshold and identify across the larger area where are the specific trees that are either dead or are severely stressed. So in this case, what we did is we used Ndvi, like I mentioned earlier, and thermal. To identify the high-risk trees, we only selected areas where the Ndvi value was less than 0.5, so lower Ndvi value, and where the temperature was also more than 30 degrees Celsius. So that's how we were able to kind of sieve the data down and identify just these 5 trees of interest or that were determined high risk. So we see these ones are clearly dead, these 4 trees. And this one looks to be, severely stressed. You can see the lighter green color in the RGB, but what was most striking in this one is that the core temperature of this tree was rather warmer than surrounding areas. So that was the primary thing that had flagged this particular tree, was the higher temperature.
Okay, Emily, and you had 2 questions about the classification and detection in the chat.
What kind of classification do you use? Maybe maximum likelihood or support vector machine. Yeah, maximum likelihood classification is what had been used, is what we've used primarily for the examples that I showed. Was the detection of treetops also carried out on the basis of the data of the multispectral camera? And what was the accuracy of such detection? And was that, so the detection of the treetops, was that for this example or for the previous example?
I'm not sure. Previous.
Okay. Yeah, the multispectral data was used for that. So that was red edge that was used to delineate the treetops, as well as using the multispectral information for the tree health analysis.
Okay, perfect.
Okay. So yeah, zooming out back to this data set, we can see those specific high-risk trees are identified. In this case, none of them were close enough to the power line close enough or tall enough to be a risk, but it shows how using those 2 data layers of the multispectral and the thermal, we're able to, over a large area, identify the few trees that are dead or dying. And then just to close out this example, this is the digital surface model from this area. So just to get a sense of where the power lines are in relation to the height of the trees. So you can clearly see here that none of them are taller than the trees, or none of the trees are taller than the power line in this case. All right, so that is the last example. I know, Annette, we talked about potentially taking a little break until more questions. We could do that, or we could go into questions if there's more.
I think if it's okay with you, we go directly to the questions.
Sounds good.
And I have a question for you.
Sure.
Can you explain more about the calibration and the plight planning? I think overlap, altitude, speed, and so on.
Yeah, that's a good question. So for flight planning, there's the first consideration would be how you're triggering the camera. So as I mentioned before, there's 2 options. If you're just connecting for your drone integration, you're just connecting the camera to power it up, and it's not connected to any kind of communication. Then you're going to need to have the camera trigger itself. So you can do that by connecting to the Wi-Fi interface. So you can use your phone, you could use a tablet, anything to connect to that Wi-Fi interface, pull up the browser. We provide the instructions with the quick start kit that comes with the camera. But once you're connected to the browser, you can see the homepage will show status indicators as to whether the light sensor is connected and powered on. It will show satellite connection for GPS lock and a couple different parameters. So that's kind of the homepage. And then the next tab you'll see is the ability to see kind of a live stream. It's a couple seconds delayed, but a live stream. So you can use that to take a manual capture with the sensor as a first check to say, okay, all 5 sensors are capturing. I'm seeing imagery show up here. So that's a check you can do. The third tab will show how you set up for triggering. So a recommendation there is to use overlap mode. So for overlap mode, you're just entering in what for the drone passes, what the overlap will be as far as the side lap and the front lap. Generally recommend 75% overlap, 75 to 80%. 80% you might want to do if the area you're looking at is pretty homogeneous looking. So to get higher overlap in those situations. But once you've set up your 75 to 80% overlap and your flight altitude information, the camera will use that information and automatically calculate how often to trigger based on that. So that's the one that we recommend most often. The other options are to do a time interval. So if you wanted to do once per second, for instance, that's as fast as the camera will be able to capture. For red edge is once per second. For ultimate, it's a little bit slower. So it's once every 1.5 seconds. So the timer mode is another option. And then external trigger mode is another option. So if you did have an autopilot system that you wanted to connect and have that be sending, pulses to the camera to set it to trigger, you could do that for a more in-depth integration. So once the camera is, you've got it set up in any one of those three ways, then you can disconnect from, the camera Wi-Fi interface and then move on to your drone mission planner. So whether it's, a DJI mission planner or, Pix4D capture is one. We have one as well called Micasense Atlas. Whatever you're using, you can move to that to actually set up the pathway for the drone to be flying. So you want to set it up with the front and side lap, just like I mentioned before, 75% overlap. For most mission planners, there's an option to add a custom camera. So for most of them, it's just a one-time setup where you enter in the parameters for the red edge or the ultim, whatever sensor you're using. And the main information there is the field of view of the camera. And so you'll need to know that for the mission planner, just so it can accurately do the overlap. So yeah, I would say, first connecting to the camera, set it up to trigger, then moving to the mission planner to move forward with the drone mission. As far as the reflectance panel, you just want to take a capture of that before and after the flight. And you can do that either there's a manual button on top of the light sensor. So you can hold the drone and press the button on the type of the light sensor, or you can, in some cases, if you've got a skyport sensor, you can just do it through the mission planner, do a capture. So that's kind of the general workflow. If you do have a skyport sensor, you can skip the step of connecting to the camera. In that case, you're just pulling up, DJI Pilot and setting up the drone mission plan and the triggering through that. After you fly and everything's done, all of the imagery will be stored on either the SD card or the USB stick that comes with the camera. So an SD card if it's red edge, a USB stick if it's ultim. So you're going to have all your TIFF files on those. And then you can use that to upload to whatever processing software you're using to go through and process into an Ortho Mosaic.
Okay. And about the altitude, did you mention that? What do you recommend, to fly close or have some distance?
Yeah, so it will depend a little bit on what you're looking at and how big the plants that you're looking at are. So generally, to cover the most area the most effectively as far as flight time, 400 feet or 120 meters is a good kind of rule of thumb that a lot of people use. That's also why we include the spatial resolution at that flight altitude. But then the lower you fly, the better that spatial resolution will be. So if you're looking at, early emergent plants, for instance, like the example I showed for ultim, you are going to want to fly lower to make sure you're going to get at least 1 to 2 pixels per plant in the image. So that would be one consideration I would think, or I would say, as far as your flight altitude, is what are the size of the leaves or the plant that you're looking at, and what is the kind of analysis that you're looking to get? Do you want to have just a couple pixels per plant to get general sense of plant health, whether it's like NDVI or NDRE? Or are you doing something that needs a higher spatial resolution like plant counting? So it will depend a little bit on what you're doing. We do have a flight calculator that is helpful for determining, at different flight altitudes, what speed to fly as well. That's another question I get a lot too, is, if you're flying lower, what speed should I be flying at? And I do recommend the flight calculator is super helpful for that, because if you're flying lower, you can enter in your desired altitude and the speed you're thinking about flying. And then you can calculate, and it'll show you the time between captures. So that's what you'll want to look at to make sure that it's feasible. Considering that the red edge can capture once per second and Ultim can capture once every 1.5 seconds, you'll want to make sure that it's, at or higher than that number. So if it's showing, 0.7 seconds between captures, that's something that won't be possible. The camera won't be able to keep up with the captures. So the flight calculator tool is helpful for determining the flight speed, as well as for showing you what the ground sample distance would be at different varying flight altitudes.
Okay, and you can find it on your website, or where do we find the calculator?
Yes, yeah, even if you just Google Micasense pre-flight calculator, it should show up, but it's on the Micasense website as well.
Okay, perfect. Thank you. And then you have 3 more new questions. The first one is from Oliver.
All right. Let me see here. What differentiates Micasense sensors to, for instance, the sensor on an already integrated system like the Phantom 4 Multispectral? Yeah, that's a good question. So I would say something that the biggest differentiator is the radiometric calibration workflow. So something like the Phantom 4 does have a light sensor. However, it's the one irradiance sensor that's more of a kind of pass-fail indicator of looking at variation in lighting conditions during the flight. So it's not going to have that, DLS2 kind of light sensor that is reading that irradiance on that second by second level, writing that into the metadata to then be used in the processing software. It also doesn't come with a panel to be used as a reference for the calibration as well. So the radiometric calibration, that's one. The other would be the integratability, I guess you could say, of our sensors. So it's not a fully integrated system in that it offers more flexibility. Whether you're using the same sensor across multiple drones, or if you upgrade the drone in a couple of years, being able to just swap the camera to that new drone instead of having to buy a whole new system. Another advantage being if you do have a drone that has dual payload capacity, being able to fly with both the multispectral and a high-res RGB, or a LiDAR system if you have a smaller LiDAR system that can be flown side by side. So the flexibility in the integration options is another differentiator. Okay, so another question here.
Yeah, from Piotr.
So usually in satellite remote sensing systems, MS and PAN sensors are used to create a composition of the so-called pan sharpened. What do you think? Would it make sense to add a pan sensor with a much higher resolution than 5 existing bands on the red edge for creating better images with higher resolution? In satellite remote sensing, this is normally expected by some users. Yeah, so higher spatial resolution is definitely something that we hear a lot of customers always looking for. So that is something that we are definitely considering, getting the higher spatial resolution for the multispectral. So I would just say stay tuned as far as what we're able to. We'll keep you updated on any new products that we come out with, definitely. Okay, another question here.
Yes.
So about the Stora Enso project, specifically. So what kind of software was used for tree health and bark beetle? That's a good question. I actually am not too sure because I know that was done in-house. So that was, I don't know, Annette, if you have more information potentially on that project and what was used.
I think they used Pix4D field to collect field data, but I don't know if you mean processing the field data. I'm not sure if it was, no, I'm not sure.
Okay, for the processing. So they did the processing first, and once they got the Ortho Mosaic, they did the additional analysis to train the models for the classification. Yeah, I'm not sure what software was used for that portion of it to do the tree health classification.
I think it was in Agisoft. I'm not sure.
Okay.
I'm not sure. Maybe we have some attendees from Stora Enso with us. I think so.
Yeah, maybe they can provide some additional information. I know there was an article written about it as well that maybe could be shared that has more information on what workflow that they used.
Yeah.
Okay. So another question.
Yes, from Piotr, flying DJI M300.
So flying the M300 with the Skyport, would you still need to connect to the DLS2 sensor using a cable? Or can you use internal DJI installations for camera and DLS2 communication? Yes, you still need to connect the DLS2 via cable to the camera below. So the triggering is happening through the Skyport, through the connection with the camera, and then we're able to connect with the light sensor through that cable. So it still needs to happen. And then Oliver had another question. Do you have any additional examples of how multispectral cameras can be used? Yeah, definitely. We've got a lot more examples on our website. Would be a good place to go to. Specifically looking at the sample data that we have available. So if you just go look under products in each camera type, for each camera type, there's a sample data section that you can click on. So we've got both raw data sets that you can download and process yourself if you want to see that whole workflow. We also have a data viewer that shows different process examples in a kind of more interactive map. So you can kind of zoom in and view the different layers. You can view RGB composite, CIR composite, NDRE, NDVI, a couple others I'm not remembering right now, but there's about 6 different layers that you can view using the data viewer to give you a sense of between, we've got red edge examples, dual camera and Ultim across a variety of different crops. And, some of it is forestry, some of it is kind of land management related. So that's a great place to look.
Okay.
And then I got a question about which band combination was used in the forest example to classify the trees. So for that one, for the Stora Enso example, I'm not sure what was used there. I believe for the classification of tree health, that was NDVI was used. For the example that I showed of the stand counting, a CIR composite was used in that case. And then a question from Alan. Is it possible to rent or try equipment for a nonprofit association that has young people as members, mostly to let them see what's possible and maybe help out with feedback and testing purely for educational purposes? Yeah, Annette, could you answer that one? Is that something that's Swedron is able to offer, doing potentially demos or offering rentals?
Yes, if it's a Swedish company or group or something, I don't think we can do it outside Sweden.
Sure.
Yeah.
Yeah, so that would be something to kind of ask your local reseller, depending on where you are.
Yeah.
Okay. Okay, great. It sounds like, yeah, she's in Sweden.
Okay,
he is
so
in Sweden.
yeah, okay. Ellen, you please send an email to us at Sweden, and we help you out. Perfect. Okay, Emily. So let's see if some more question comes, or maybe we should do some. I think the question has ended. So I take the opportunity I want some help for you attendees with a small survey. If you click on the link in the chat, and please answer a few questions. And we hope we can do some more webinar in the future, Emily, to have more use case to show for you and discuss.
Yeah, definitely. Feel free, for any attendees, feel free to let Swedron know as well if there's additional examples that would be useful. We can always see about doing a follow-up webinar.
Yeah. Do you have something to say about the future? If you have some new products coming, or planning something, a webinar or something?
For this year, the product lineup that I shared is what we have. So that's what we have, this year. We'll definitely update you as we have, we're always working on new sensors. So as we have more information about those, we'll definitely share that as it's available.
Okay, perfect. So if you doesn't have something more to give us, Emily, and if there are no more questions, I think we say thank you to you to being here with us and sharing us some information.
Yeah, definitely. I was glad. Appreciate all the questions, and glad to discuss with everybody today. So I hope the content was useful. Thank you for hosting as well.
Oh, thank you. So I think we say goodbye then, and we soon meet again, I think, and I hope.
All right. Yeah. Thanks everybody for your time.
Yeah. Thank you so much. Bye.
All right. Bye-bye.
Bye.